Okay, so this is an interesting Webassign problem. So basically what we have is a wire carrying a current, and the wire is moving in this direction with the velocity v. And it's a distance x from this coil here, which has a current going through it as well. And so actually it doesn't have a current, never mind. So basically we're measuring the rate of change of the magnetic field, or magnetic flux, which, as we all know, it only exists if there's movement. Basically what we have is there's a magnetic field around this wire, something along those lines. Right hand rule, so it's going this way. Sorry, I'm so messy. But basically, it's going counterclockwise here. And now there's going to be magnetic flux on the coil and an induced current, because we've got a magnetic field that's moving. So basically, these are the answers, and now I'm going to explain how to do it. So this is the equation that you're going to use and turn into the rate of change of the magnetic field, which is what we're trying to find. We have to take the derivative of it. This is just differentials, and basically it doesn't really make sense because velocity is necessary to induce a current. Basically it's necessary that there is velocity in this, so that would be the dx over dt, listed right here. So that's why it's important that we expand it. As you can see, it doesn't actually change the value of it. It's just you're adding the dx. It would cancel out, but that's besides the point. And then after that, it's just math. Pretty easy. You plug it in. Remember to keep track of the units. That's something a lot of people forget to do because they don't really care about understanding it. They just care about plugging in the numbers. And you end up with Tesla per second as your dB dt, the rate of change of the magnetic field. So now over here, your magnetic flux, epsilon equals the rate of change of the magnetic flux over time. You rearrange it, you end up getting this equation, which then is going to have dB dt. Plug it all in, use the answer you got there, and then you get that, and it's in volts. Right. Now, for part C, which is the direction of dB dt, it is into the page because this is the, as you can see, the magnetic field here is into the page, and the direction of the curly electric field in the coil, this is the negative dB dt, so that is so the rate of change in the magnetic field is basically, well, you can just, it's always kind of difficult to do, so you basically just worry about negative dB dt. So that is going to be out of the page, and then use the right hand rule. And that's counterclockwise.